All right, let's get started. Hello, everyone. Good morning. So today we are still discussing about the interface to a database management system. The relevant chapters are still number 3 and 5 in the Ramakrishnan and Gerke book. So in the last lecture, we have seen a couple of ways how we can analyze data in our database via SQL queries. Quickly fix that. Yes. So, so today we're going to see a couple of more advanced queries. But before we do this, a little reminder about what we have seen last time. Last time, we have seen queries that correspond to the format that you see here. We are specifying data sources from which we want to use data in the from clause. Then we specify conditions that the result rows should satisfy in the where clause. Then we specify how we want to partition our data into groups in the group by clause. And in the having clause, we can specify conditions that those groups should satisfy. All right. And finally, in the select clause, we are specifying which are the columns that we want to see in our results. So many of those parts of the query are actually optional, but this is the things that we have seen in the last lecture. All right. Now, before we go any further, because we haven't seen many examples yet for this type of query, we're gonna do a little bit of data exploration. If you do data exploration, then you first of all want to have a data set. So one possibility to download such data sets is the Kaggle website, for instance. And if you look under the data tag, then here you have data sets about various topics. So I recommend you to perhaps choose one or two of them, download them, and run a couple of SQL queries over them to get a hang of it, which is what we're about to do now. All right. And here specifically, since we want to load those files into a database, we can, for instance, restrict things to comma-separated value files that we can easily import into our data set. And it seems to be a slight problem with the interface here. Okay. All right. Now, I spotted so just before the lecture, I spotted a data set that I wanted to use for this demonstration. And here it is. That is a data set about video game sales. And we're going to use it in order to run a couple of simple queries over it. So let's first of all download the corresponding data. All right, we have downloaded it. And now I'm copying that data. Okay. Here you can see my console. And the data set that we are looking at, it looks like you see here. So we basically, we have values separated by commata. The first row of the data set that you see here. That is essentially the headers of the different columns. And after that, you have the associated data rows. So I just want to guide you through the analysis of one simple data set. So after we downloaded it, we want to create a database in order to import the data. So for instance, we can create this database over here. Now we log into the database. And so the first thing that we would do in order to analyze such a data set is to create a table in order to import the data. And we have already seen the command for that. So let's create this table over here. We have the columns that we want in the table essentially given in this file over here. So for instance, here, we first of all have a sales rank, which is apparently of type integer. Then we have a game name, which is of type text, it seems. There's the platform of type text, the year of type integer, game genre of type text, the publisher. Then first sales column, which seems to be of type numeric. Sales in the EU, this is in millions of units, by the way. That is also numeric. Sales in Japan. All right, and now we have created this table into which we want to import the data, and we have already seen the command for that. So if I want to import the data from a file, I simply write this copy command with the name of the table and then the name of the file, which is vgsales.csv. Now we are telling the database that here we want to import a CSV file. And we tell database that values are separated by comma type, could be a different character. And what you also often want to specify is how those null values that we will talk more about today. Null value essentially means a value that is unspecified, and you need to know how those null values are specified, and then you need to tell the database about it. And I believe in this data set, it should be one null value should be represented as N and A. And also here, we have one header row, and that is also important for the database management system to know. So I'm writing that here. And now let's load that data into the table. And I think maybe the way in which null values are represented, it might be this way around with the backslash. Let me quickly check that. All right. All right. So that was the right representation for the null values. I got it wrong. Now we have loaded the data. The database management system tells us that we have loaded about 17,000 rows. And if we want to, first of all, inspect what we have just loaded, we would write something like select all columns from that table and loading all the rows that can be a little bit too much data. So one small new feature that I wanted to introduce today, that is the limit clause, and that works essentially just by specifying how many rows you want to show in the result of a query. So if I write this, then I get a much more reasonable output. And on first view, that looks okay. Let me quickly increase the size of this window a little bit, then it becomes easier to see. So, all right, so this seems to be the data that I wanted to load, everything fine. All right, and now the last time we have seen different queries for aggregation and grouping and so on. So now I can perhaps apply some of that to this data set over here. Perhaps the first thing that I might be generally interested in is how many of those games people sell in total. And I could express this as a query where I'm summing over the global sales of those games. And the data source is, of course, still the vGames table. Now, if I do this, then I find that in total, about 9 billion units are sold here. That is interesting, but perhaps I want to make it a little bit more precise. I want to break down those sales into different categories. And you can do this exactly with the group by query that we have seen last time. So perhaps what I want to do here is that I group by the genre in order to see which types of games sell better than others. And if I do this, then that's not going to be very useful here. If I do this, then I essentially just would get the numbers here, but I wouldn't get which genres those numbers are associated with. So what I probably want to do is that I also put the genre into the select clause here. All right, and here I have the different categories of games with the number of units sold in millions. And yeah, it seems that certain categories of games, they are significantly more popular than others. In particular, sports and action games seems to be quite popular. All right. Now, another thing that I could do is to group those games, for instance, by the platform for which they have been produced. And I want to know how many units have been sold for different platforms. So I can do this like you see here. Perhaps this is a little bit more data than I actually wanted. I see there's like data for 31 platforms. And maybe I want to focus more on the important ones. And here there is a great question in the chat. Somebody is proposing to order them. And you can absolutely do this. And that is a second feature that I wanted to introduce today. Let me do this in a second. For the moment, I wanted to propose a different solution to how I can reduce the number of platforms for which I retrieve data. For instance, here, I could introduce a count statement and only retrieve data for those platforms where the number of titles is above a certain threshold. Now, here essentially, since we use the group by clause, this query is grouping data by the platform. So one group is defined by one specific platform. And if I want to narrow it down to platforms that have certain properties, that is a condition on the groups. So I must put that condition into the having clause. And now let's experiment a little bit. For instance, if I set this threshold, that might be too restrictive, but here essentially I narrow it down to platforms for which we have at least over 100 titles. All right, and now this narrows it down already quite a bit from 31 to 20 rows. Maybe I can narrow it down even further to only the most common platforms. Yes, and now we have only relatively common platforms. So that is how I can narrow down things, but the different possibility would be to order things. So instead of using this conditional to prune out groups associated with platforms that are less commonly used, I could also say that I simply order the results by the number of sales, for instance. And then I would know where in the result to look for those platforms that sell more titles. So here, for instance, I could also write order by count. And I want to order in ascending order. So I'm putting this ask abbreviation here. So if you do this, then as you see here, I tend to get the platforms that have more titles and are also associated with more sales, more units sold, rather later in the query. And if I want to get them first instead, then I can use the desk keyword instead. So here, now we are starting with those platforms for which I tend to have more titles. And as opposed to the count, here I could also use the sum again. And now I will get first those platforms for which I have lots of global sales. And here another proposition is whether it wouldn't be better to first sort and then to limit the number of output rows, right? You can also do this and that works perfectly. That is a good suggestion. So here I'm first sorting and then later I'm narrowing it down to only the most common platforms. So the advantage of this one over the query with the having clause that I used before is that with the having clause, I have to decide what kind of threshold I should set. And a priori, I might not know what makes a good threshold. So if I want to narrow it down to a fixed number of rows at most, then this type of query here, where I first sort by something and then I limit to something, that is probably preferable. All right. And here there's a couple of questions. And so the limit clause is applied at the very end. That was a question here. And people have also posted a link to the data set, thanks. That is the correct one. And the count ordering is indeed the number of rows. Okay, good. So this is just a couple of simple queries that I can run on this data set. And I just wanted to show you the complete cycle from how we download the data set to how we import it, and then how we can run some simple analysis queries over it. So I encourage you to do that as well, perhaps not with this data set, but with a different one. There's lots of choice on Kaggle or on similar websites. All right. Now you should be able to see my slides again. All right. So we have started with a reminder for the type of queries that we have seen last time. And we have applied that. We have also added 2 new features. Now the first feature that we added is the order by clause, and then we added the limit clause. I have already demonstrated how that works, but here's a little bit more details about the syntax. So the order by clause, and as you see, it comes after the having clause, if you have any. The order by clause allows you to specify a list of order items. And each order item consists of a column according to which you want to sort, and a sorting direction, which can be ascending or descending. Now, this statement ensures that the output of your query is sorted by those columns that you specify here. So in order to determine the sorting order between different result rows, the database management system, we first look at the first order item that appears in your order by clause. And then for those rows which have the same value in the first order by item, it will look at the second order by item and sort by that. And if it also has the same value there, then it will look at the third one and so on. So the priority for sorting is on the items that appear earlier in your order by clause. And there was some question about in which order things are applied in general. For the order by clause, it is applied after the where condition, for instance, is evaluated, and also after grouping has happened. And that is important because if you have a group by query, then into the order by clause, you can only put columns that are guaranteed to have the same value for any group. So basically, you can only use columns in the order by clause where all rows in the same group are guaranteed to have the same value. And that means that as long as we're talking about columns, those essentially must be columns that appear also in the group by clause, because if a column appears in a group by clause, it is guaranteed that all rows in a group have the same value for that column, because that column is used in order to define groups. So this is a bit similar to the restrictions that we had for the select clause. Once we have a group by query, then there's also certain constraints on what you can put into the select clause. You can also only put columns into the select clause, for instance, that are guaranteed to have the same value for all rows within a group. And that also means that in practice, we want to restrict it to columns that appear in the group by clause. All right. Now the limit operator, that one is pretty intuitive. I simply give the database system the maximum number of result rows, and then this limit clause is applied at the very end of query evaluation. All right. Now in the following, we're gonna discuss more and more advanced features of SQL queries. First of all, I want to discuss a little bit more about null values. Now, we have already quickly mentioned null values a couple of times. A null value in SQL simply means a value that is currently unspecified, for instance, because it is unknown. Now, those null values, for instance, influence the way in which SQL evaluates Boolean conditions. Typically, you would think of those Boolean conditions as evaluating either to true or false. But if one of those conditions contains a null value, then the overall result of the expression could also be unknown. And we will see a couple of more concrete examples for that in the following. Now, this is how you can essentially check for the evaluation result of one of those Boolean expressions. You can check whether it is true or whether it is false. Careful, if you want to check whether the evaluation result is null, whether the evaluation result is unknown, you cannot simply write equal to null, but you need to write is null in order to check for that. And then if you have any rows in your data that where the condition in the where clause, for instance, evaluates to null as opposed to true, then those rows will not be contained in your query result. Now, let's make a couple of concrete examples. I encourage you to try out at least some of those examples, either in your local Postgres installation or using the website that I have shown you last time, which doesn't require any local setup. Perhaps the first one, we can do it together. If we have a query of the form that you see here, where we want to know whether 3 equals null. Does anyone have propositions for what the result of this query could be? Syntactic error, okay. That would be one possibility. It's a little bit more permissive than that, actually. Okay, there's different propositions, null, empty, okay. So does anyone to explain in the chat, please, why they think, for instance, that the result could be a syntactic error? or why the result could be null, for instance. Okay, perhaps typing out an explanation like that, that takes a little bit more time. So let me resolve that. So the correct answer here would actually be null. And I expected that perhaps some people write false as a proposition, but that has not happened. I guess one could at first view think that the result here could be false because I have an equality condition and I have different things on the left side of it and on the right side of it. Now the problem is this. Those null values represent an unknown value. So they are placeholders, so to speak. That means if I write a 3 equals null, it essentially asks whether 3 is equal to some unspecified placeholder. But the placeholder, as it is unspecified, we cannot be 100% sure that it isn't 3 by coincidence. So here I'm essentially asking whether 3 equals to some unknown value, and whether that is the case depends on that unknown value. And since we cannot decide whether this is true or false, the answer to this query would indeed be null. Okay, and there's a couple of other examples here. Yeah, and somebody is posting how that looks like in Postgres into the chat. So those null values in Postgres, they're just represented as empty spaces. So here you have one row, but you don't see any content, and that's because this row only contains one null values. So null isn't a value like in other languages like Java. So there is some differences between Java null values and SQL null values. I mean, in particular, you couldn't perform certain operations with Java null values because at some point you might get an exception, null pointer exception from the Java system. So here in SQL, in principle, you can use null values wherever you can use other values as well. The only thing is that if you have a null value somewhere, it might mean that if the null value is contained within one expression, it might make the result of the entire expression unknown, meaning null in the end as well. And null is like false in this case, so that it depends on which case you are referring to. In some cases, so if you are referring to the semantics, if you have a null value as a result in the where clause for one specific row, then I fully agree having a null there is treated in the same way as if the result had been false. So if the entire condition in the where clause evaluates to null, then the corresponding row will not be included into the query result. All right. So, okay. So now maybe you had a little bit of time to try out some of those examples. I believe it is relatively quick to try because you don't need to type a lot. And yes, so we have already discussed about the first one. The second one is also null as a result because we are essentially asking, is one first unknown value the same as one second unknown value? And of course, it depends on the unknown values. The third query, null is null. That is always true because is null is checking whether something is unknown. Then in this case, it is indeed unknown. The next query is the opposite of that and therefore false. Now, perhaps the last two queries are still interesting. We have true or null. And in this expression, we do have a null value appearing. However, an or expression is true as soon as at least one of the components is true. And in this case, one of the components definitely is true. Therefore, the end result does not really depend on the unknown value, and therefore the end result of this should also be true. On the other side, for the last query, we have true and null. That means if the unknown value is also true, it makes the entire expression true, but if the unknown value is false, it makes the entire expression false. So the result depends on the unknown value, and therefore the result is also unknown. So this is what is called SQL's ternary logic, because all logical expressions can have three result values: true, false, and unknown. And the question is, what should select null? Is null do if the predicate is true? This query, frankly, is not very useful, admittedly. So this is just for the sake of an example. In practice, this query, it's not interesting. It essentially has a constant result, right? And by the way, also note that here we are not using any data source in order to calculate the result of our query. So we don't have a from clause. Depending on the database management system, some of them disallow that. You always need a from clause, but in Postgres, you can write queries like that that do not depend on any data in your database, but just evaluate constant expressions. All right. Now, and the is keyword, quick question here still. So the is keyword, it is more precisely the is null expression. So that essentially checks whether the expression on the left-hand side of it evaluates to null or not. And it is true only if the left-hand expression evaluates to null. So null equals null is null, but null is null, that is true. All right. So it is basically not only the single is keyword, but it is null. That is a fixed command. Both words together. All right. So now that we have discussed in more detail about null values, we can discuss more about some extended variants of the join. So far, we have been looking at joins that essentially retrieve pairs of rows from two tables that match together, meaning that they satisfy some kind of join conditions. For instance, we have seen the example where I'm pairing up the students with the enrollment information for the courses that they are enrolled in, and I'm always matching together those rows which have the same student ID. Now, one problem with that is that it eliminates rows in a table which don't find any matches in the other table. Those rows will not appear in the join result. So if I'm, for instance, joining students with enrollment information, then a student who hasn't enrolled into any courses yet will not appear in the join result at all. And this is not what I want in some cases. Perhaps I want to, for instance, encourage students to enroll for courses who have not enrolled yet. But in order to do that, I first of all need to make sure that those students remain in the join result such that I can see that they haven't enrolled in any courses yet. And SQL offers you some specialized syntax in order to make sure that the result of a join keeps all the rows that appear in the input tables, even those rows which do not have any matching rows in the other table. And that is called an outer join. Now, for instance, for students and enrollment, the result relation of the join between students and enrollment contains columns for the student ID, for instance, but also columns for the course ID, for the enrollment. And the question is, if we want to keep those students without enrollments in our join result, what should we fill in as values for the course ID column? And this is where null values come into play, because those outer joins will fill in the values for rows without matching rows in the other tables. They will fill in those missing values with null values again. So if you have those students who haven't enrolled into any courses yet, then the course ID and the corresponding join result will be set to the null value. This is the syntax that you can use here. You can write in the from clause of the query some first table, left outer join, some second table on some join condition, and that is guaranteed to keep all the rows of the table on the left side of this join. There's also the complement, the right outer join, where we say that all the rows on the right-hand side of the table are kept in the join result. And if you're interested in keeping the values, the rows for both tables, you can also use the so-called full outer join. And very quickly, I'm gonna show that to you. So if we have, for instance, so if we log into the university database where we have those tables with students, courses, and enrollment, then we can, for instance, select all columns from the students, left outer join with the enrollment information. And here I should still add the join condition, which is on the student ID. All right, and here you see the result of this join. Now here, for instance, a student Bob seems not to be enrolled in any courses. That is why the course ID is left empty in Postgres, and that always indicates a null value. And here, by the way, I had also inserted before a student with unspecified student name. So that's why here we have the student ID for that student, but the name has not been assigned yet. And also that student has not been enrolled in any courses. That is why we have empty fields here as well. So this is how the result to an outer join looks like in Postgres. Now back to the slides here. So so let's also see a little example here in the slides. One thing that I might want to do, for instance, I mean, especially, for instance, if I want to remind students who have not enrolled in any courses yet, what I want to do is perhaps to count the number of enrollments for each student. And in the following, we will see how we can do that with an outer join. So here for the moment, we are using the same database that we have used in the previous lectures of students with enrollment information and courses. And as you see, for the moment, we're not using any outer join. We are using a standard join. And that means that students without any enrollment would be filtered out by this query, which is not what we want. So already we probably want to replace this join by a left outer join that is guaranteed to keep information about each student. But now the problem is that we are currently using a count statement, and I just see that some group by statement in this query has been left. So here I actually want to add a group by statement for the corresponding query. So that unfortunately has dropped. So here we want to group by the student name in order to count the number of enrollments for each student. And the problem that we still have here is that for the moment, we are counting the number of result rows. That means for those students for which we don't find any matching enrollment information, we will still count one result row for those students, which is not what we want, because for those students, we want to count 0 enrollments. So the last thing that we need to do in order to make this work is that we replace the count star, which counts any result row, by count CID, which only counts those result rows that have a non-null, meaning a noun value, in the course ID column. So if a student doesn't have any associated enrollment information, then after the outer join, that student will have null values in the course ID column. And if we use this counting variant, then those rows with null value for the course ID will not get counted. So I will get a count of 0 for those students who have no enrollments yet. All right. So this is some useful join syntax that in practice, every once in a while, you might need some of that. I'm also going to post the corrected example on Piazza. Now, in the following, we're going to look at a little bit more advanced SQL features. And one powerful feature of SQL is that you can write queries which combine multiple other queries together. So you can essentially write a composite queries that essentially combine multiple smaller SQL queries in one way or in another one. And the easiest way probably of doing that is with the SQL set operations. So if you have results of queries, then for instance, sometimes you might want to take a union of the result of 2 queries. And with SQL, you can do this using the union or union all keywords. And essentially here in this specification, query 1 and query 2 refers to queries, for instance, like the ones that we have seen so far, but then you can compose them using the union keyword, for instance, into a larger query. And the result of that query is essentially the union of the results of the 2 contained queries. What is important here is that those 2 queries, query 1 and query 2, they must be compatible, meaning that their results have the same structure. So it has to have the same number of columns and also the same column types. There's a couple of different variants. If you use the union a keyword, for instance, then SQL will automatically eliminate duplicate rows that appear in the union result. If you use union all, for instance, then it will keep any duplicate rows. So you might have the same result row multiple times. You also have operations for intersecting the results of queries and for taking the set difference between 2 query results. But in all of those cases, you must be careful because the result structure of those different queries that you are combining with the set operations must be compatible. All right. And a priori, there's a question about whether the order will be kept when using a union. So in general, without putting the order by clause, you are not guaranteed anything about the result order. So if you want a specific result order, then you can still use the order by clause. And by the way, some of those operations here, some of those set operations, they are, for instance, not supported in some other common database systems, but if you try it with SQL or with the website that I have shown, then you will be able to run those operations. All right. Now, another thing that we will start discussing today and finish at next time probably is that we can essentially not only combine queries with set operations, but we can essentially use so-called nested query in many other parts of a query as well. For instance, so far we have seen that in the from clause of a query, we can refer to tables that appear in your database. But instead of that, you could also write a new query inside of the from clause. And we will see some examples on that. Also, for instance, you might use queries as part of a condition in the where clause, and so on and so forth. So in general, since queries take SQL relations as input and produce SQL relations as output, you can compose them together in various interesting ways. Now, if we have the situation that we have one large query which is containing a smaller query, so to speak, then we also call that a contained query the subquery as opposed to the containing query. It has different variants of that containment. In the simplest case, the contained subquery is essentially self-contained. So you could run this query independently and it would work with your database management system. That is what we call an uncorrelated subquery. But for more complex expressions, you can actually make the subquery refer to elements outside, to elements of the containing query. And those cases are a little bit more difficult to understand. That is what we call correlated subqueries. Now in the following, we're gonna first discuss about the uncorrelated subqueries, which are a little bit easier to understand. And we start with a rather trivial and frankly not very useful example here. So we simply want to select the names of all students. Then I can, of course, simply use the students table in the from clause. But just to illustrate the principle of subqueries, I can also put a new subquery into the from clause, as you see here. So here, essentially, I have one entry in the from clause, which corresponds to a subquery. It's an entire query right there. And what it does is essentially just selecting the student names from the students. And then the result of that subquery is named SQ for a subquery. And as you see in the select clause of the query, for instance, I can refer to the name for the subquery that I have just introduced. So that is important. Postgres actually will force you to assign names for subqueries that appear in the from clause, because typically if you use tables in the from clause, then you always have a name. And I can use that name in order to refer to specific elements from other parts of the query. But if I write a new subquery, then a priori it doesn't have a name yet. So Postgres forces you to specify a corresponding name. And so how that is handled depends a little bit on the database management system. In each case, this query is not yet very interesting, admittedly. So let's see something a little bit more useful. And here we have a subquery in the where clause, for instance. And what we are doing here is that we are selecting the names of students where the GPA is greater or equal to the maximum GPA among all students. So here we are selecting the students with the highest GPA. And here we essentially use one subquery in order to calculate the largest GPA over all students with the maximum aggregation function. And then we are using the result of that query within a condition in the where clause. And here the question is whether the result of that query would not be just one student. That depends actually, because multiple students might have the same GPA. And very good, I see somebody is giving that same reply. So in general, by the way, so I think this is great. I see that often there's some discussions in the chat. I want to encourage that. I often see great replies to the answers from other students. So please feel free to post not only questions, but also replies to the questions of your peers in the chat. I think this is working very well. All right. So this was the first example for subqueries. And here things are already becoming a little bit more useful. So today I wanted to take a little bit of time to show you how to apply SQL in order to actually analyze, do at least some simple analysis of a data set in practice, the full cycle basically. I encourage you to try it out yourself. So I mean, SQL, it's something which is a little bit like a programming language in that it is much easier to understand it if you are experimenting with it yourself. So I encourage you to do that. Now, the next time we're going to see a little bit more advanced features of SQL, in particular when it comes to subqueries. And then we are going to start with a new chapter. We're going to start looking at how the database management system internally processes your queries. All right. Thank you and have a nice day.